All right, welcome to The Explainer. Today we're jumping right into a pretty high-stakes engineering mystery, a dangerous, powerful shake that can threaten some of the biggest rockets ever built.
And get this, these massive rockets, like the European Ariane 5, can be seriously rattled by tiny, invisible swirls of gas. These vibrations, or oscillations, can feed on themselves and become a huge problem, but their source is buried deep inside the incredible chaos of a rocket motor. So how in the world do you solve a problem you can't even see? Well, you have to become a detective. Today we're following the investigation, using some pretty complex computer simulations to hunt down the exact cause of these hidden vibrations. All right, let's get into it. So, first things first. To catch a culprit, you've got to recreate the scene of the crime, right? For rocket scientists, that means building a model of the inside of the motor. But, one that's safe enough to study up close. And this is our crime scene, a cold gas experimental setup. It's built to mimic the exact shape and gas flow of a real solid rocket motor. Gas gets pushed in through the walls, just like it would if solid propellant were burning. The really clever part? There's no actual fire. That gives scientists a perfectly clear view of all the forces at work. So at the very heart of this whole mystery is one key player, the vortex. Just think of it as a tiny little whirlpool of gas. Now, one of these on its own, totally harmless. But when you get thousands of them working together, they can pack a serious punch. The investigation pretty quickly narrowed things down to two main suspects. Basically, two competing theories for where all these disruptive vortices were actually coming from. Okay, so suspect number one is something called obstacle shedding. The idea here is that the vortices are created when gas has to flow over some kind of internal barrier, like the joint between two segments of fuel. Then you've got suspect number two, wall shedding. In this theory, the vortices are born right along the chamber walls, created by the friction of all that gas being injected. And here, this is where it gets really interesting. We've got our first piece of surveillance footage from the simulation, and you can see both suspects caught in the act. Right there, behind the obstacle at the top, you can see vortices peeling off. But look down along the bottom wall. You can also see these longer vortex structures forming right where the gas is being injected. So what happens next? We let the simulation roll forward. And these vortices don't just drift along. They travel down the chamber, and you can actually see them starting to pair up, merging into bigger, more powerful swirls. And this is where the real danger starts to ramp up. These newly formed super vortices keep moving down toward the rocket nozzle at the very back. And here is the critical moment. When these big, organized pockets of gas slam into the nozzle, they generate a pressure wave, an acoustic pulse, basically a sound. Okay, so we've seen our suspects in action, but which one is the real troublemaker? To figure that out, we need to analyze their acoustic fingerprints, the unique sound frequencies they each produce. All right, let's check out the evidence. On the left, you're looking at the fingerprint for the obstacle vortices. You can see they start out at a really high frequency, 530 Hz, but then as they merge, that frequency shifts. But then you look over at the wall vortices on the right, and it's a completely different story. You see two super strong, consistent peaks right around 240 and 290 Hz. Now, this is where things get really dangerous. That sound wave that's created when the vortex hits the nozzle doesn't just vanish. It travels all the way back up to the front of the motor, and it actually encourages the creation of more vortices at that exact same frequency. It's a lot like when you blow across the top of a bottle. That sound you make actually encourages the air to vibrate at that exact same pitch, creating a steady tone. And this diagram just illustrates that vicious cycle perfectly. Vortices travel down, they hit the nozzle, and that sends a sound wave traveling back upstream. This whole thing locks the system into a powerful, self-sustaining oscillation, and that's the dangerous shake we're trying to stop. But, just when the scientists thought they had this thing all figured out, boom, a major plot twist. When they compared their super clean simulation data to the messy, real-world experimental data, things just didn't quite line up. Just take a look at this comparison. The simulation, that's the solid line, it predicts these incredibly sharp, clean spikes in pressure at very specific frequencies. But the real experiment, the dotted line, it shows a much broader, kind of messier signal. The simulation was, it was too perfect. It was missing something crucial from the real world. And that missing clue? It was turbulence. The first simulation assumed what's called a laminar flow. Think perfectly smooth, like honey pouring slowly. But inside a real rocket motor? No way! It's chaotic, it's messy, it's turbulent. So the scientists went back and started adding what they called pseudo-turbulence into their model. And just watch what happens. As they crank up the turbulence from 0 to 2.5, then to 5%, the frequency fingerprint of those wall vortices changes completely. Those sharp peaks broaden out and shift, and suddenly it starts to look a whole lot like what they saw in the real experiment, a much, much better match.
And here's the smoking gun, the hard numbers. The original simulation without turbulence was predicting a pressure oscillation that was 10 times higher than the real experiment. But as they added turbulence, the simulated value dropped like a rock, getting so much closer to the real-world measurement of 0.025%. This was it.
And with that, the verdict was in. The paper itself says it best. Wall instability represents the dominant source of acoustic energy in the flow. So it turns out it wasn't the big, obvious obstacle after all. Nope, it was the subtle, messy, turbulent friction happening all along the walls. That was our main culprit.
So let's just quickly recap what we found out here. We learned that there are a couple ways these vortices can cause trouble, and that computer simulations are absolutely vital for hunting them down. But the big reveal was that the wall shedding was the main problem, and the real key to cracking the case was realizing just how important turbulence is. And all of this work, it directly helps engineers build safer and more reliable rockets for the future. You know, this whole investigation managed to uncover one of these invisible problems. But it really makes you wonder, doesn't it? As we keep building bigger and more powerful rockets, what other invisible forces are out there, just waiting for us to find them?